Okay, you can see my last slide. We talked about the sign convention for conduction in flowing last lecture, right? And I hope you understood this sign convention, right? And once again, I repeat, the reason why we use minus sign in the Fourier equation is because we want Q positive in positive x direction. That's why that minus sign is put there, right? Maybe in coming lecture, maybe the today's lecture or the next lecture, you'll find the problems where I'll be testing your understanding of the sign convention itself. So moving further, what is one-dimensional heat conduction? So I want you to draw this diagram first. One-dimensional heat conduction. So consider a slab like this, the way it is shown on the screen. In most of the Indian author books, you will find they have given this 2D sketch like this slab. Whereas intentionally, I have written this 3D sketch. Reason over the period of maybe last 4-5 years, I found that the students struggle in understanding some terms out of this one-dimensional heat conduction. That's why I have used this 3D sketch instead of using the 2D sketch like this. So draw this TX plane first and then show this rectangle and then draw this the remaining part. So consider this as a slab or something like a brick, right? And let us say this is the thickness. Even though the notation we are using L, consider this as a thickness of your slab. The temperature of the left face of the slab is T1 and the temperature on the right face is T2. Forget about this distribution for time. Temperature is function of x alone, which is written here. This is of course true for one-dimensional steady state heat conduction. We'll talk about Weissenberg form of heat conduction equation later on. So time, you just draw this diagram and then show the direction of this Qx double dash. Now I already mentioned that temperature on this face is higher compared to this. So that's why we know the direction of the heat transfer will be from high temperature to low temperature. That's why it is shown like this. Fine. And use the notations like consider this W as the width of your slab and H is the height of your slab, and this A is the area normal to the direction of heat transfer. A is the area normal to the direction of heat transfer. So now you see this is the phase through which the heat transfer is taking place in the x direction. The direction is shown like this. So the area which is normal to this arrow. So if I show this part, this one, or if I try to show the face which is at the back end, so it will be like this. So maybe this face, right? So the area of this face or this both are same is nothing but the area perpendicular to the direction of the heat transfer, right? Now I am going to apply the Fourier's law of heat conduction to this situation, and I will derive the expression for what is the heat flux flowing through this particular simplest case of one-dimensional heat conduction. So you can see Qx double dash is the heat flux, which is given as minus K dt by dx. We know this. Then I am evaluating what is dt by dx. So first of all, find out what is dt by dx. dt by dx is written as, now see, I am always writing the next temperature or the final temperature minus initial temperature, right? So 2 is used for the final suffix and 1 is for the initial, right? So I am writing this temperature gradient as temperature difference is T2 minus T1 divided by dx. So dx is what? The length or the thickness of this slab, right? So if I say this is x1 and x2, then at this condition x is equal to x1, which is 0, and here x is equal to x2, which is L, right? Or you can simply say x2 minus x1 is L. So that's why instead of writing this as x2 minus x1, I have directly written it as L. So the temperature gradient dt by Tx is written like this. And now I'm going to put this expression here and rewrite this equation. Qx double dot is minus k T2 minus T1 divided by L. And solving this further, I can write the expression like this. I already know that temperature T1 is more than T2. So this minus sign I am just absorbing here. And then I'm writing Qx double dot is k T1 minus T2 by L. Or this temperature difference T1 minus T2, I am simply writing it as delta T, overall temperature difference delta T divided by L. So Qx double dot can be written as k delta T by L. And once I know the heat flux, then I can find out the rate of heat transfer Qx, which is based on our definition of the heat flux, which is this Qx divided by A, the heat transfer per unit time or the rate of heat transfer per unit area is nothing but the heat flux. So based on that I can find out the rate of heat transfer Qx once I know the heat flux. So this is how we have analyzed the one-dimensional heat conduction through plane slab using Fourier's law of heat conduction. In the coming lectures, what we will do is we'll derive the general heat conduction equation in Cartesian coordinates, and we will also try to use the differential form of the heat conduction equation and apply it to the simple case, and still we will be in position to derive the same expression which we have derived using the Fourier's law of heat conduction. Clear? So note down these expressions and then we will go to the next slide. So remember, what is the area across the flow area here, or the area normal to the heat transfer? Remember this. So this is that area. In examination or maybe in oral examination, I will ask what is the area. So if I ask them to shade it like this, what generally students do, I will tell you. They say, if I draw this 2D sketch like this, and if I ask them what is the area normal available for the conduction heat transfer, they will shade this front face and they will say this is the area A, which is wrong. Huh? See, this is the front face area. No heat transfer is taking place in this plane or this direction. So it is taking place normal to this face. So that's why this is the area normal to the direction of heat transfer. Now you understood why I am using 3D sketch here?
Yes, sir.
So to make you understand that the area involved in that expression is not this one, rather it is this face. Correct? Okay. So can I go to next slide now?
Sir, just a minute.
Now, based on this analysis of one-dimensional heat conduction in case of plane slab, we will solve numerical based on the formula which we have derived. Very simple numerical, but it will give you an idea of how to approach a solution for a particular problem. There is systematic way to analyze the heat transfer problem, and we will give the general guideline how the problem should be solved. And 90% of the time, the steps which I am going to talk about can be followed. 90% of the times, I'm saying. 10% variation.
Done, sir.
Fine. The first numerical in heat transfer. The wall of an insulated furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watt per meter K. Measurements made during steady state operation reveal temperatures of 1400 K and 1150 K at the inner and outer surface respectively. What is the rate of heat loss through a wall that is 0.5 meter and 1.2 meter on the side? So the dimensions of this furnace wall are given. So how to solve this. So now I am going to display here the approach how you should solve this. 5 to 6 steps are involved there, and try to follow all these steps while solving the numerical, and you will get the better idea. So we will use this 6 steps approach to solve the in general any kind of heat transfer problem. 6 steps. So first step, you will try to find out what is known in this, or you will note down what is given, right? First step. Then in second step, you will note down what they asked you to find. For example, what they asked in this case, what is the rate of heat loss to the wall? So they are talking about what is this Q or QX for that matter, the heat rate of heat loss. Then the next step is you will try to draw the schematic diagram for this problem. So if you try to plot the diagram, so it is something like you have a wall, and this is the inner wall, let us say, inner wall of your furnace, and there is the heat available which will be taken by this inner wall, and let us say this is the outer wall of your wall, outer side of your wall, right? Inner and outer side. So the heat transfer will take place from this hot region to the inner wall, and from that it will be conducted through this slab or the wall, right? And it will go to this direction, so inner to outer wall. So it's a similar kind of diagram you can draw. If you try to draw the 3D sketch, it will be better because all the 3 dimensions are given. So this furnace is constructed of 0.15 meter thick fire clay brick. So this is the thickness of your wall, and this is made up of the bricks like this, and this thickness is 0.15 meter, right? And what are these 2 dimensions? These 2 are nothing but the dimensions in other side. Like this, you can try to draw the diagram, and this is nothing but the height of your wall, and then the other dimension, this one. So this is nothing but 0.5 meter, let us call it as the width of your wall. Fine. And then they have mentioned the temperature of the inner face of the wall. So this is the inner face of the wall. Here you can write the temperature is 1400 K, call it as T1, and the other side temperature, this side of the wall temperature T2 is 1150 K. So you can note down all these minute details in the diagrams. So schematic representation of the problem. The next step is the assumptions. If any assumption you are making, for example, you may consider that there is only one dimensional heat conduction taking place through this wall. Means heat is transferred only in this direction, not in any other direction like this. It is transferred in only one direction. So this is the assumption you may note down if required. They have also said that the steady state operation, its temperatures are stable after some time after some duration of time. So steady state is reached, right? Then you will analyze the case using the whatever the form of the equation. In this case, you may use the Fourier's law of heat conduction, and at the end you may comment on the results. For example, in this case, you may say that the direction of the heat transfer is from this case to this, or the direction of the heat transfer is in the right direction, something like that. Fine. So this 6-step approach we are going to use. Now here I have already noted down for you what is given. So in case of the first point, what is known is they have mentioned that the steady state is there, then the wall thickness is given to us. So the area of the wall is known. How the area of the wall is known? What should be the area in that case? Is it H into W, or this L is the thickness, let us say. Fine. So what area should I take? The area normal
H into W.
So it is H into W, right? So this is given. Then the thermal conductivity K of the material is given, right? And the temperatures T1 and T2 are given. Thermal conductivity K is also given. Say this is K. Temperatures, these two temperatures. Then the thickness, which is L, and this is your width and height, right? This part is known. Now what they asked you to find out the rate of heat loss, Qx you have to find out. Now, schematic can go for 2D or 3D diagram. So I have used the 3D diagram there. Then the assumptions, if any, so they already said that the steady state and one-dimensional conduction. I already explained what is one-dimensional conduction, and even K is also constant, which we are going to assume. See, K may vary with temperature T. So this is called as the case of the system with variable thermal conductivity. We will talk about this variable thermal conductivity in the coming lectures. For time being, you just assume that the K is constant and it is no more function of the temperature. So K is same or is independent of temperature. For time being, you just assume constant K, right? And in analysis, we are going to use the Fourier's law. I already talked about this. And in comments, you will make the comment about the direction of heat transfer. I already talked about this. Representation of your problem. So you have a slab like this, or the furnace wall having this thickness, this L, then the height 0.5 meter, the width is 1.2 meter. I have taken opposite, right? Doesn't make any difference actually. Or be consistent with these notations, we'll use the same. Make this as width and this as height, right? So we will use the same notations, the one which are given in the diagram. So consider width as 1.2 meter and the height of the slab is 0.5 meter. So this is your inner face of the wall and this is the outer face, right? So the heat transfer should take place in this direction. This is shown, right? So the wall area will be this area, or the back face you can see this area. Now use the Fourier's law and find out what is the rate of heat transfer, Qx. Find out. So Qx is minus K A dt by dx. We know this, right? So find it. So minus K is what? What is the K value they have given? Bolo.
1.7, sir.
1.7.
1.7.
So the area is 1.2 into 0.5. 0.5. And what is the temperature difference? dt by dx. So it should be T2 minus T1 divided by L, right?
Yes.
So it is 1400 minus 1150. 1150 है ना?
सर आपने T1 minus T2 दिया है सर.
Okay. So 1150 minus 1400, right?
Yes.
Always write
Yes.
it as T2
0.15.
divided by 0.15, right? Now see, this minus sign and this minus will become plus now, and the sign for Qx will be positive. Now what is the value of Qx now?
Sir, 1700 watt.
Watt. So your final answer is 1700 watt. And what is your comment about the direction of heat flow?
Sir, from system to surroundings.
Sir, positive. Positive.
So
Positive to the x direction.
Is Qx is positive along x direction, right? Means furnace, the heating is taking place on this side of the furnace, not on this side. So this is inner wall and this is outer wall, right? So if I put the furnace on this side, then it will be reverse, right? So when we talk about the direction of heat transfer, don't forget this part. How you are measuring the length or the, what you can say, the thickness of your slab.
Sir, can we say that heat transfer takes place from inner to outer surface?
Correct. Because inner face will be the hotter, no? So heat transfer by conduction will take place through this wall, and from the outer wall, if there is fluid in contact with the outer wall, then there will be convection. Clear? So right now we are only talking about the conduction through the slab, nothing else.
Yes.
Can I go to next slide now?
Yes, sir.
Yes, sir.
Now we'll talk about the mechanism of the convection or the physical mechanism of convection, how the convection takes place. We talked about the conduction and we understood what is the physical mechanism of conduction in case of solids, liquids and gases, right? So you just tell me a few words which describe the mechanism of the conduction in solids, liquids and gases.
So in convection, the particles move the heat from one particle to another.
I asked you about the conduction. Just tell me those words
Sir.
which we talked about in the morning, like collision, right?
Sir, medium.
Rotation, rotational motion, or the vibrational motion, or lattice vibrations, right? Or free electrons, how they contribute to the mechanism of conduction, right? And now talk about the convection. So the convection heat transfer is basically made up of two mechanisms. The first is the energy transfer by the random motion of the molecules. This word is important. This line is important. The random motion of the molecules. And second mechanism is the energy transferred by the bulk motion of the fluid. Now, what do we mean by bulk motion of the fluid? I already described this. Bulk motion of the fluid means a lot of the fluid molecules or the particles they will move together. The bulk motion of the fluid, right? Now, the term convection is used when referring to cumulative transport. So when these both mechanisms are there, so that time we generally we call it as a convection. Means the heat is transferred by the random molecular motion as well as the bulk motion of the fluid is existing. So in that case, we generally call it as the convection part, right? Or convection heat transfer. And the term advection refers to the transport due to the bulk motion of fluid alone. So if there is only the bulk motion of the fluid taking place, then we generally call it as advection. However, the more customary term is the convection, where both mechanisms of the heat transfer are appearing together. The random motion of the molecules as well as the bulk motion of the fluid. Now, look at this diagram and try to understand what we talked about in the previous slide. So we have the hot surface like this. This is a hot surface or hot plate. You can see it. And this Q double dot is the heat flux which is going out from this plate. The direction X is shown. And what this dotted line indicate? Do you remember what is this from fluid mechanics background? What is this?
Boundary layer.
So this is boundary layer, right? Or rather, very specifically, I would say this is which boundary layer?
Thermal boundary.
Thermal. In fluid mechanics, you have studied thermal boundary layer.
No, sir, in heat transfer you told thermal, na, so.
No. In case of fluid mechanics, you must have studied the formation of the boundary layer, which is we call it as a velocity boundary layer or the hydrodynamic boundary layer, or not?
Yes, sir.
So this is a velocity boundary layer which I have shown here. This one, fine. And why the velocity boundary layer exists? Who is responsible for this? Who is responsible
Viscosity.
for formation of boundary layer? Viscosity. How viscosity is responsible for this?
Zero speed at the boundary layer, at the bottom of the boundary layer.
So here U is 0 and here U is at this point. This U is U infinity, right? Free stream velocity. And in between this U is varying, right? So as you go away from the wall, the velocity is increasing, and at this point the velocity U will become 0.99 times the free stream velocity, right? So this is what you have studied in boundary layer, no? Or not? So the velocity gradient exists within the boundary layer. Velocity gradient. So whenever we have the velocity gradient like this, we talk about the velocity boundary. What happens if I talk about if we have the temperature difference? Then there should be temperature gradient or not? Temperature gradient. Correct? So look at this diagram now, the right hand side diagram. So we have this y plane again, I explain as it is. And this red line shows the temperature distribution. This line shows velocity distribution. How u is varying with y. As you go away from the wall, how u is varying. So what this line indicates is, as you go away from the wall, how the temperature is varying with respect to y. Right. So at this, the surface of the wall, this temperature is nothing but Ts, surface temperature of the plate itself. So this length indicates temperature of the surface, right? And as you go away from the wall, the heat is transferred from the wall to the surrounding fluid, right? And you'll go on, if you go in y direction, you will find the more and more heat is transferred, and this is how the temperature of the temperature gradient is established. So T infinity is temperature of the fluid, right? And Ts is the temperature of the surface. And here Ts is greater than T infinity. So there will be the heat transfer taking place from the wall to the fluid, surrounding fluid. So, and how this will happen? This will happen by the convection, because we know that when there is a surface which is in contact with the fluid, and if there is temperature difference, then the convection will occur. Is it clear? So the two things you must understand. One is the velocity boundary layer. So here the velocity gradient we'll talk about in case of velocity boundary layer, and in case of the thermal boundary layer we talk about the temperature gradient. This temperature gradient. Get me or not? Temperature gradient. Now this is the temperature is varying along. How should I write it? Should I write it as dt by dx or dt by dy? Then tell me.
dt by dy.
Because it is varying along y direction. Fine. Clear?
Yes,
so
sir.
this diagram must be clear to you. No? So up till now we were talking about only this kind of the velocity distribution and the boundary layer. Now in coming lectures, when we talk more about convection, we'll take into account this kind of boundary layer also, which is the thermal boundary layer, and how the temperature distribution is established in case of the thermal boundary. The classification of convection heat transfer, we already talked about in the introductory part, that convection is basically classified as free and forced convection, or natural convection and forced convection. So what we mean by forced convection? When the flow of the fluid is caused by external means, such as by a fan, or by a pump, or a blower, or any atmospheric winds which are typically moving at the speed of 5 meter per second, this 5 kmph to 15 kmph, or even more than that. So those will cause the forced convection. So the essential part of forced convection is what? The fluid motion is assisted by some external agency like fan, pump, blower. Right? Then we call it as a forced convection. Convection or free convection. Now the flow is induced by the buoyancy forces or density differences basically. So if there is density difference, then the flow will be established, means the fluid which is light in weight will move upward, and the fluid which is more in weight or dense will move downward. And this is how the convection currents will be set. And the flow of the fluid established in this sense due to density differences will cause the natural convection. So for example, if I put some hot plate in the room and still air, and nothing is, the fan is not switched on, So this will get eventually cooled down on its own, right? Now how does this happen? Because of this free convection. We are not forcing the air to move over this plate, but when the air comes in contact with the hot surface, this density difference will be established, and this density difference will drive the heat transfer in this case. So this is example of the free convection or natural convection, right? So the buoyancy driven forces are responsible for the free or natural. Now I am going to put forward 4 examples on this slide where you can decide what type of the convection is taking place. Look at the first diagram now. So what you see is let us say the electronic PCB is there like this, which is hot, and the heat is transferred from this hot surface to the surroundings, and there is surrounding air here, but this air is forced by some fan like this. So this fan is forcing the air over this PCB. So what type of heat transfer this is? So this is case of forced convection because fan is there, forced convection, and what it takes out from the surfaces with sensible heat. I hope you understand. You already know what is sensible heat and latent heat. You have studied right from your 10th physics to even thermodynamics also. What is sensible heat? What is sensible heat and latent heat?
Sensible heat, there's temperature difference.
And latent heat?
Enthalpy difference, no temperature difference.
Is it? Okay, at the end of the slide, you will automatically come to know. At the end of this slide, you will automatically come to know what we mean by sensible heat and what we mean by latent heat. So the first example is forced convection, where you are extracting the sensible heat. The second example, now same PCB board is there, but now it is the orientation is changed. So this is made vertically here, right? Fine. And now this time the fan is not there, and the air, surrounding air, comes in contact with this board, and still there is the convection heat transfer, Q double dot. The heat is transferred from the board to the surrounding, but this time this heat transfer is driven by the density differences or buoyancy driven flow, you can call it. So this is an example of a natural convection. This is an example of a free convection. So in this case also free convection, but what you are extracting is only the sensible heat. Sensible heat is taken out from the PC. Clear? Now the third example. Now look at this. So what you see on the screen is a pan which is kept on a hot plate like this. So the heat is supplied through this hot plate to the water which is there inside this pan. And now this water is boiling. What you see, the small droplets of the vapor bubbles here. These droplets are nothing but the vapor bubbles. And what you see in this zone is steam or a vapor, right? Can you see that?
Yes, sir.
So what kind of convection is this? So this is boiling. So boiling is a special case of convection where you are talking about both sensible as well as the latent heat. Fine? Boiling. And now look at the last example. What do you see on the screen now? So there is a pipe, and what is going through the pipe?
Cold water.
So the cold water is going through this pipe, and there is a moist air surrounding this pipe. If you look carefully at the diagram, the temperature of the moist air is more than the temperature of this cold water, right? Hear me or not?
Yes, sir.
What will happen in these cases? The heat will be transferred from the moist air to this cold water. That's why this direction is shown here. Heat will be transferred from the moist air to the cold water, and in doing so, whatever the moisture is there in the air will get condensed on the surface of this tube, right? And you can see the droplets like this, or not, water droplets. Now this is example of again the convection heat transfer, but this time it is condensation. So the condensation where we talk about the sensible as well as the latent heat. Is it clear?
Yes,
Hello?
sir.
Yes, sir.
Yes,
So,
sir.
Yes, sir. Yes, sir.
so now there should not be confusion, which is the free convection, forced convection, and where the sensible heat is and where the latent heat is. So latent heat we talk about whenever there is change of
Phase change.
Phase.
Phase
very
change.
good, change of phase or phase
Phase change
change is
at
there.
constant temperature.
At constant temperature, phase change may be boiling or condensation. So water boiling at 100 degrees centigrade, right? Or steam condensing at constant temperature. So that kind of situation. So remember, boiling and condensation both are reforms of the convection. Okay. Now moving further, we'll introduce the second law in case of heat transfer, which is typically given for the convection part. The Newton's law of cooling. You must have studied in physics, 11, 12 physics or not. What is Newton's law of cooling? What is Newton's law of cooling? What is Newton's law of cooling?
सर रेट ऑफ टेम्परेचर डिफरेंस सर मतलब सराउंडिंग के टेम्परेचर से मतलब वो प्रोपोर्शन होता है.
So I may say like this, that the heat flux by convection is directly proportional to the temperature difference, right? So this is what is
सर
shown.
उसमें सिर्फ लॉस ऑफ हीट होता है ना सर, मतलब उसमें तो लॉस ऑफ हीट से डील किए थे हम लोग, तो सर यहाँ पे हीट ट्रांसफर में सर मतलब दूसरे बॉडी में गेन ऑफ हीट भी होता है ना.
Same thing we are talking about, the temperature difference. So it may be Ts minus T infinity or T infinity minus Ts. Get it or not? See, as long
Yes,
as
sir,
there is
yes.
temperature difference, the heat transfer will take place. So the heat flux by convection is directly proportional to the temperature difference between your surface and the surrounding. This is what we have written on the screen. So you can write down this formula. Qx double dot is proportional to Ts minus T infinity, where Ts is the surface temperature and T infinity is the ambient fluid temperature, you can call it as. Now, we have replaced this proportionality sign by some constant small h. So write down the second expression, Qx double dot is h Ts minus T infinity, where this h is called as the heat transfer coefficient or convective heat transfer coefficient, to be more precise. Simply call it as a heat transfer coefficient or convective heat transfer coefficient. If you refer any Indian author books, in 99% of the time you will find they simply write the heat transfer coefficient. People do not make an attempt to write it as a convective heat transfer coefficient, because not a single Indian author you will find who has mentioned about the radiative heat transfer coefficient. So you can formulate the expression for the heat transfer by radiation in such a way that you can represent this quantity in case of radiation also. In that case, we will call it as a radiative heat transfer coefficient. So time being, you just remember this h is nothing but simply the heat transfer coefficient or convective heat transfer. So note down all these notations. So Qx double dash is a heat flux, the rate of heat transfer per unit area, heat flux by convection. Unit is watt per meter square, as it is from the previous discussion. Qx is the rate of heat transfer, which is again given in watt. Ts is the surface temperature. You can take it in degrees C or Kelvin. It doesn't make difference because we are talking about temperature difference. Then the T infinity is the temperature of the surroundings. Same logic as that of the temperature of surface. And H is the convection heat transfer coefficient or convective heat transfer coefficient. Unit will be watt per meter square K. So you just rewrite this formula as H is Qx double dot divided by Ts minus T infinity, and just put the units for these quantities, and you will get the unit as watt per meter square K for the heat transfer coefficient small h. You take any book on heat transfer, you will find the symbol which is used to represent the heat transfer coefficient or convective heat transfer coefficient is small h. Any book. Now, can I go to next slide?
Yes, sir.
Yes, sir.
Further, I will just put the table here only to make you understand what is the typical range of the heat transfer coefficient which you may come across. So the process is mentioned on the left hand side, and the value of typical values of the heat transfer coefficients are given, or the range is given on the right hand side. So if you have the free convection or natural convection, when gases are involved, so that time you'll find the typical values of the heat transfer coefficient will range from 2 to 25. 2 to 20. Now, if the same free convection takes place where liquids are involved, you may come across the values of heat transfer coefficient ranging from 50 to 1000, right? And if we talk about the forced convection and take the same medium like gases and liquids, then in case of gases with forced convection, the heat transfer coefficient values will range from 25 to 250. And in case of liquids with forced convection, these values may go as high as 20,000. So will range from 100 to 20,000. Forced convection with liquids and gases. And the phase change phenomena, that is boiling and condensation. Boiling and condensation, phase change phenomena. As I already talked about, it is nothing but the convection. So in case of boiling and condensation, you will find the values of heat transfer coefficient may be going up to lakh also, 1 lakh. Right from 2500 to 1. So the highest heat transfer coefficient values are observed in the phase change phenomena, which is boiling or condensation. And as you go towards the gases, the lowest value of heat transfer coefficient is observed in free convection with gases. So at least you must remember the typical range for the heat transfer coefficient. Not exactly the numbers, but you should at least know the range. That's why I have projected this table on the screen. Fine. Now
Sir,
the
do we
question,
have to verify the problems by getting these values?
not necessary, not necessary. Now reason why I'm telling you not necessary is, see, sometimes we may use the data from the books which are which may not be standard. So in that case, you will find that they have mentioned the values of the heat transfer coefficient H greater than 25 for gases. Then you will come back and ask me, sir, it is not fitting in this data. Then what should we do, right? So that's why I said this is typical range. Is it clear? But
Yes,
if you have the standard text on heat transfer, 99% of the times you will find the values will fall in this range only. Clear? And few exceptions should be acceptable to us. Clear?
Yes.
Yes, sir.
Now the question which I am going to ask or raise here is, why to talk about the H values right now? Why to talk? Why is it so important that I am straightway introducing the heat transfer coefficient in the very second or the third lecture of the heat transfer? Because this term has got huge importance, the heat transfer coefficient H. Now, if you talk about the convection as a whole phenomena, now pay attention. The sole aim of studying convection is to find out the value of heat transfer coefficient H. Remember this. You use any technique or any method our aim is to find out, always aim is to find out the heat transfer coefficient value H for that particular situation. And once we know the heat transfer coefficient H, then we can find out what is the rate of heat transfer or what is the heat flux if you need for that matter. So all other quantities can be of interest, can be calculated if we know the heat transfer coefficient H. So the sole purpose of studying convection is to find out the heat transfer coefficient H. I repeat, the sole purpose of studying the convection heat transfer is to find out the value of heat transfer coefficient H by any means. Now there are different ways by which you can find out this heat transfer coefficient H. Typically 5-6 methods are there. We'll talk about those methods when we start the module on convection heat transfer. Clear? Now can I go to next slide?
Yes.
Yes, sir.
Yes, sir.
Now the last mechanism of the heat transfer, which is, or the mode of heat transfer, which is the radiation. So we'll talk about the mechanism of heat transfer by radiation. So what is radiation? So in case of radiation, we know that the thermal radiation is nothing but the energy is emitted by any matter which is at non-zero temperature. I talked about this in the previous lecture. So any material or the surface will emit the radiation when it is at non-zero temperature, right? Second point. Although we will focus on the radiation from solid surfaces, emission may also occur from liquids and gases. So why this point is given? Because you should not be under impression that the radiations are emitted only by solid surfaces alone, right? So emissions may be emitted by liquids as well as gases. Now next point, regardless of the form of matter, means whether it is solid, liquid or a gas, the emission may be attributed to the changes in the electron configurations of the constituent atoms or molecules. So the configuration of the material matters a lot when you talk about the emission. Next point, the energy of the radiation field is transported by electromagnetic waves. We talked about this previously based on the electromagnetic wave theory or simply wave theory, or alternately by the photons based on the photon theory. So how the energy comes from the sun, we talked about these two things, that is wave theory and the photon theory. Next point, the radiation does not require the presence of material medium. I already explained this. In fact, when there is a vacuum, this is the effective way of the heat transfer. Radiation is the more effective way of the. And next point, just now explained that in case of the absence of the material medium, means in case of vacuum, the radiation heat transfer will be more efficient way of the heat transfer. Clear? These are the 5-6 points you should remember about the radiation. Now we'll talk about the radiation exchange. So let us take this heading into account now. The radiation exchange at a surface and between a surface and large surroundings. So I am going to project two diagrams for this. We will divide this statement, radiation exchange at a surface, and then second between the surface and large surroundings. So let us say if I have a computer, a screen in this room, and this entire room is surrounding this computer, so I will take it as a large surrounding. Then how the radiation exchange will take place between these two, my computer screen and the surrounding, let us say, or the room. Or simply I may talk about the radiation exchange of, let us say I have a table, the flat surface of the table, and how the emissions are going out from this flat surface. I may talk about these two. Now look at this diagram. So this first diagram talks about the radiation exchange at a surface. So this is a surface having the surface emissivity epsilon. Note down these symbols. The surface emissivity epsilon and the absorptivity alpha. What is absorptivity? You must have studied in physics. The fraction of the energy which is absorbed by the surface, right? So let
तो
us
ब्लैक बॉडी वाला
absorptivity alpha, and then the temperature of the surface is Ts, right? So just try to draw this
Sir.
diagram.
So is it same as the coefficient of absorption and emission?
You
Like that?
used to call it as the coefficient of absorption, reflection,
Yes,
something
yes.
like that. So same
Yes.
thing, absorptivity, emissivity, and reflectivity. So right now we are talking about the absorptivity symbol. I'm using alpha for that. And then the gas, which is at temperature T infinity, and the heat transfer coefficient is mentioned here, small h, right? Then G is the irradiation, means the total radiation which is coming to the surface. E is the radiation which is emitted by the surface. And apart from this, the radiation exchange, there can be the convection taking place from the surface to the surrounding. So that's why this term is added, Q dot double dot convection. So the heat transfer by convection or convective heat flux, Q double dot convection. So similarly, I can say.
So what is G?
G is called as the irradiation. Irradiation means it is the total incident radiation falling on the surface, right? So this is the radiation exchange at a surface. Now look at this formula. You have already studied this in physics, right? So you must have studied Stepan-Boltzmann law that the emissive power of a black
Yes, sir,
body
yes.
is directly proportional to
पढ़ा सर
the earth power of its absolute temperature, right? So note down this formula. So EB is given as EB is equal to sigma into Ts raised to 4. What is this sigma? What is this sigma we call it as? What is sigma?
Sir, it is something surface related.
It is Stepan-Boltzmann constant. This is Stepan-Boltzmann law, no? So the proportionality sign is replaced by this constant sigma. Stepan-Boltzmann constant. What is the value of Stepan-Boltzmann constant?
Sir, 1.6 raised to something 10 raised to minus 24.
No, it is 5.67 into 10 raised to power minus 8 watt per meter square K raised to 4. I thought you people must be knowing all this from your the physics background, 11th, 12th physics background.
Yes sir, थोड़ा भूल गया sir.
Okay, ठीक है. Anyway, write down these two formulas. EB is equal to sigma Ts raised to 4, and for non-black body, this emissive power E will be equal to this epsilon sigma Ts raised to 4. So the emissivity is nothing but this ratio, E upon EB. So emissivity is emissive power of a body, ratio of emissive power of a body to the emissive power of black body at the same temperature. So emissivity is E by EB. So if I use this formula, then I can write that the emissive power of any body, E can be written as epsilon sigma Ts raised to 4. So if you are done with these two formulas, I will project the second diagram. Shall I go ahead?
Yes sir, done with. Yes.
Now look at this. Now same kind of surface is taken here, a similar kind of plate having the temperature Ts, but this time this plate is surrounded by a large surrounding like this. So this surrounding means whatever the energy which is coming out from this surface is intercepted or is confined by this surrounding. And within this surrounding, there is a gas which is at temperature T infinity, and the heat transfer coefficient H is also mentioned. You understood difference between these two? So previous diagram, we had only the two temperatures, temperature of the surface, temperature of the fluid T infinity or the gas. And in this case, we have three temperatures now. The temperature of the surface, which is greater than the surrounding. This is surrounding temperature, T surrounding, T sir. And the T infinity gas temperature is already there. So you understand this? Huh? Hello? Hello, am I audible?
Yes, sir.
Yes, sir.
Note down this relation. The temperature of the surface is more than the surrounding temperature, and it is also more than the temperature of the gas, which is close to this plate. Is it clear? And apart from this Q dash convection, Q double dash convection, there is one more term now added, that is Q double dash radiation, right? And here what we are assuming is the surface is having the emissivity epsilon, which is equal to absorptivity. See, this epsilon is equal to alpha. This is what we have assumed. Emissivity is equal to absorptivity, and the area of the surface is capital A, and the temperature is Ts, right? And now we will write the expression for this Q double dot, the radiation. Write down this expression. Q double dot radiation is nothing but the heat transfer rate per unit area. So that's why Q by A it is written, right? And this must be equal to, now this is the net the heat transfer by radiation. So it is the difference between these two quantities. What is this irradiation? Part of it is absorbed. This is the total incident radiation falling on the surface. So part of it is absorbed. So alpha G is absorbed by this, right? Absorptivity is alpha, right? So you have to deduct this from whatever the emission which is going out. So the emission which is going out is given by this expression, epsilon sigma Ts raised to 4 minus the absorbed radiation alpha G. G is the irradiation. And how you find out the irradiation? Write down this formula. Irradiation G is given as sigma into T surface raised to 4. See the difference. This temperature is not Ts, it is T surface raised to 4. Temperature of the surrounding to the power 4. So G is given by sigma T surrounding raised to 4, whereas the emissive power E is given as epsilon sigma Ts raised to 4. And then you will get this formula. So Q double dot radiation is epsilon sigma Ts raised to 4 minus T surrounding raised to 4. Now there is the slight confusion here. This term, don't think that this is product of EB and Ts. So this indicates that emissive power of a black body is function of the surface temperature, is function of, read it like the function of, and then this whole is replaced by this term. So don't read it as EB multiplied by the temperature Ts. Is it clear? Hello?
Yes, sir.
So you will substitute this term here.
Yes, sir.
So EB will be replaced by this sigma Ts raised to 4. This term. And E, relation between E and EB is known to us. So if you want to find out what is E, this E, you have to multiply by this epsilon. So that's why epsilon is there. So this whole term is nothing but E, capital E. Is it clear? I hope it must be clear to you now. And now just substitute for this G and for this term EB from here, and then you will get this formula that the radiation heat flux Q double dot radiation is equal to epsilon sigma Ts raised to 4 minus T surrounding raised to 4. And I think we are running out of time. We should stop now. Continue our discussion from this slide onward in the next lecture. Just let me stop recording first.